Okay, in the previous video, we learned how to evaluate the hydrostatic force on a plane surface. We also learned how to evaluate the location of that resultant force on that plane surface. In this video, we're going to extend this concept to the hydrostatic force on a curved surface. So here what we have is an arbitrary surface S. We define here n the surface unit normal, which always points outwards from the surface. The hydrostatic force on an elemental area would be defined, as before, as dF is equal to minus P, which is the local pressure, multiplied by the outward normal. And you have the negative sign here because the outward normal is in the opposite direction to the direction of the pressure force, which is always acting against the surface. So this dF over here, this differential force, is applicable at a very particular location. That is, you will have a dF over here, dF over here, and all of this depends on your local pressure field. All right, so let's consider this curved immersed surface. Okay, so we have some sort of tank, and on the rightmost edge, we can see that it kind of forms perhaps a quarter circle, but we're trying to keep it fairly arbitrary at this point. So we've defined a coordinate system xy, and again you see this dF, this differential force, which is acting against the surface, and it is locally defined as well. We also define a coordinate system S, which goes along that curved surface. So that coordinate system S will depend on the functional definition of the surface geometry. So to calculate the total hydrostatic force, one would perhaps do something like the total hydrostatic force would be the summation of all the individual forces on that curved surface. And again, so what we're trying to find is some resultant force, perhaps somewhere acting along here, which we would call F, or if we want, FR for resultant. So we've defined what this differential force is. So we integrate over the surface, and we have our unit outward normal multiplied by the local pressure multiplied by the differential area, where the differential area would be something like the length of the element ds multiplied by the dimension into or out of the page. So this would take the form of a double integration where we have np, and our dA would take the form of ds dz, where ds is our segment length over here, and z is defined into the page. So we would integrate between 0 and s and 0 and z. So we would try to find some sort of functional definition for that curve that defines the curved surface, perhaps trying to parameterize it as a function of y, let's say. However, we could say that this is not always defined. Or the double integral, maybe we'll just write gets messy really fast. So it gets messy really fast for non-straightforward functional definitions of your curved surface S. So instead what we can do is that we can just do a simple force balance. Okay, so what we would look at is only the fluid volume that is in contact with the curved immersed surface. So this would look something like, we would have something akin to a quarter circle, but I'm not stating that it is necessarily a quarter circle. And again, we have our coordinate system xy. And so what are the forces acting on this volume of fluid? Well, this volume of fluid will definitely have a certain weight. So we'll write this as Fg for the force due to gravity. Okay, so this, again, I'm calling it a quarter circle, but it's not necessarily so. So this quarter circle of fluid, let's say water, has a certain weight associated with it. This is a body force. Now remember, this is a free body diagram that we are doing. So we want to look at all of the forces acting on this. So this is the free body diagram of the fluid, not of the curved surface. So we are looking at all the forces acting on the fluid. So we know that the surface will exert a force on the fluid. And this force we could call this force Fr, which is the one that we're actually looking for. Similarly, recall that you have this entire amount of fluid to the left of the fluid volume in contact with the curved portion. So recall that you're going to have a pressure distribution that looks something like this. And we've studied this when we looked at hydrostatic forces on a curved surface. So this distributed pressure force will have a resultant force. And so we could write it as, we'll just write this one as F1. Okay, so this is the pressure force applied by the fluid to the left of the quarter circle on the fluid volume defined by this quarter circle. So all we now have to do is evaluate our force balance. So we know that the sum of the forces in the x direction will have to be equal to 0. These are hydrostatics, so we are not looking at fluids in motion. So we know that F1 minus Fr in the x direction will have to be equal to 0. Similarly, in the y direction, our sum of the forces will have to be equal to 0. We've defined y as being positive downwards, so Fg, our force of gravity, will be positive minus the y component of our resultant force. And recall that this Fg, force of gravity, will be equal to rho multiplied by the fluid volume multiplied by g minus Fry. And now let's just look at F1 here. So F1 we will take from our knowledge of the resultant force on a plane surface. So this was in the previous video. And so this surface over here, it's an imaginary surface, so it's not a solid surface, but it is a plane surface. And therefore, as we saw, the resultant force on a plane surface is equal to gamma multiplied by the area of that plane surface multiplied by yc, which is the location of the centroid of that plane surface. So if we define this dimension here as h, and let's say that it has a dimension into the page of w, then we can write F1 as rho g multiplied by the area, which will be W, H, and then multiplied by YC, which will be H over 2. So we'll have H squared over 2. And this will be our F1. So all we will need is some sort of definition of what this curved surface actually is, and this will help us find the volume here in order to calculate the weight of the fluid. So let's consider an example on the right of your page here. So we have an open tank. So recall that this little triangle here, this inverted triangle, means that it is open to the atmosphere. We have an open tank containing water, and it has a bulge in its vertical side that is semicircular in shape. So we have a semicircular protrusion on the right side here of radius of 3 feet. And this protrusion, it begins 6 feet under the surface of the water. And so what we want to know is we want to find the horizontal. So we want to find the horizontal and vertical forces on the bulge due to the water. So again, we will adopt a similar method. Okay, so we're going to consider the fluid that is in contact with the curved surface. So we're going to have a weight, Fg. There's going to be a force, which we'll just call F1. And this force is due to all of the water to the left of this half circle. We'll have a horizontal force from the curved surface onto the water, and similarly a vertical force, Fv. So this is the free body diagram on this semicircle. And we'll define a coordinate system as follows, with x to the right and y positive downward. Okay, so let's look at F1. So F1 is the force on this fictitious plane surface here. So recall that this F1 will be equal to the specific weight of the fluid, which is water, multiplied by the area, multiplied by the location of the centroid. Okay, so the location of the centroid, so this is a plane surface. There's nothing particularly special about this. I should probably state that The depth inside, so I don't know if we were to try to draw it this way, is 1 foot. So this plane surface, this red plane surface on which F1 acts, is just a rectangle which has a depth of 1 foot and a height of 3 feet. Okay. And recall in our derivation of this resultant force that y is defined as having its origin on the free surface. All right. So here we're working in feet, so we're in imperial units. The specific weight for water is 62.4 pounds per cubic feet. Then multiplied by the area, so as mentioned, this area is going to be 6 feet by 1 foot. All right, so 3 feet is the radius, so it would actually be 6 feet. I mentioned 3 feet by accident earlier. Okay, and now the location of the centroid with respect to y is equal to 0. So y is equal to 0 is at the surface, so the centroid is located here, which would be 6 plus 3. So 6 plus 3 feet. So this force here is equal to 3,370 pounds. The weight of the fluid, Fg, is simply the specific weight multiplied by the volume. So again, we have the specific weight of 62.4 pounds per cubic foot multiplied by the volume. So here we have a half circle. So this, for a full circle, it's pi r squared. So this will be pi multiplied by 3 feet squared divided by 2. Okay, so we only have a half circle. So now we have the area, and then we have to multiply it by the depth, which is 1 foot. And this results in 882 pounds. So, to satisfy equilibrium, what we would find is that Fg should be equal to Fv. Therefore, Fv is equal to 882 pounds. And I'm putting this arrow here to say that it is acting up. So the result is positive, meaning that our assumed direction for the force by the curved surface onto the water is indeed acting upwards. Similarly, F1 should be equal to Fh. Therefore, Fh is equal to 3,370 pounds and acting to the left. So note, however, that the above values and directions were obtained from a free body diagram of the forces on the fluid volume. However, we are asked to find the force due to the fluid on the curved surface. So from Newton's third law, this would suggest that the forces on the curved surface have the same magnitude but opposite directions. That is, the forces on the surface, and we could just call this Fx, and this would be equal to 3,370 pounds to the right, and Fy would be 882 pounds acting downward. And this result makes intuitive sense. Okay, this is a vertical column of water with a protrusion, and so you have a weight of a fluid plus a pressure acting on the left-hand side, And so you would expect that the curved surface is experiencing some sort of downward force due to the weight of the fluid and the pressure. And so this result does make intuitive sense. So this is generally the approach that we take for finding the hydrostatic force on a curved surface. And this approach, again, is based on a force balance on the fluid volume in contact with the curved surface. And this helps alleviate some of the difficulties in integrating, especially if the curved surface is complex and the integration is not easily performed.